Hello everybody, it's Mr. Record again from Avon High School. I'm going to talk a little bit in this video about the various ways that a particular function's limit would fail to exist. And really, if you're watching this, you're probably a beginning AP calculus student. In fact, this is something that we do in class the very first day. Oftentimes I don't get to go into the detail with these three reasons as much as I'd like to. So I'm going to go ahead and make this video, and I'm going to illustrate three separate examples of where a particular function's limit would fail to exist. And for those of you who are in my particular AP class, we're talking about examples 3, 4, and 5 from the section 1.2 notes. So we've got these three reasons, 1, 2, and 3. Number 1, the function f of x would approach a different number from the right side of a c than it would approach from the left side. And we talk a lot about when you find a limit, you use your fingers, trace along the curve, and if your fingers come pretty close together, say they meet at an open circle, a discontinuity, a hole, then you could go ahead and say that that limit does exist. But what if your fingers totally come together or approach one another, but do so to two different y values? And that's what we're going to take a look at. So I'm going to back up here to example 3. And we're going to look at a really common type of function, the absolute value of x divided by x as x approaches 0. And before I start, obviously you can tell that this is going to be a numeric type of limit, hence the reason why we have the, oops, not ready for the Nspire there yet. We have the boxes. And we're going to go ahead and fill those in right now. We're going to go ahead and say, okay, x is going to approach 0. So we totally understand that if we put 0 as our target there right in the middle, then, well, what does that mean? Well, yeah, let's just try to plug in a 0 for x and see what happens. We get the indeterminate 0 over 0 form, which for all intents and purposes is undefined. And if you recall, in my particular class, and a lot of teachers will do the same thing, is we would like to get as close to this 0 as possible, one on the left side and one on the right side. So we'll pick values that we typically will sort of behave like the 1,000th unit away, the 100th unit away, and the 10th away from that particular 0. And we will do the exact same thing on the opposite side. Now, there is no law that governs that you must use these particular values of x, but if you stick to these values of x, you're going to be pretty successful in finding your limit just about every time. Okay? We have yet in my particular class to discuss the formal definition of limit, but when we do, that will shed a little bit of light in terms of exactly how close to 0 do we have to be assured that the limit is what it is. Okay, so now that we've got that taken care of, we are ready to jump over to our TI Nspire. For those of you outside of Avon watching this video, we do use the Texas Instrument TI Nspire calculator. We're going to go ahead and we've got our function already set to go here. If not, you obviously remember that to get to that entry line, you hit Control followed by G. And the math template here next to the 9 is a very powerful tool on the TI Nspire. In this case, it will allow us to have a nice fraction template, and we're going to have to revisit that fraction button, the math template, I'm sorry, again, and just below the fraction, we notice that, hey, we do have an absolute value option. So we're going to choose it. Then we have our absolute value of x. Cursor down to the denominator, throw in the x, and then we can hit enter. And we have a nice function, absolute value of x over x. I'm going to move this guy out of the way just a little bit. I like to look at this graph. I'd like to sort of address, in this particular instance, a little deficiency that we're seeing on the calculator. If you take a look at the endpoints here and here, we need to all understand that those would be open circles. I can definitely make the Nspire show those. I'm not going to worry about that instant right now because it really has nothing to do with our limit. But since we know that we cannot let x be 0 at any moment, then there should not be any value defined there. But going back to our limit, if we tried to let our fingers do the walking, we would know that, hey, as our fingers travel along this blue graph, these two separate lines, and they approach this y axis here in the middle, we're going to find out that our fingers are going to pretty much be too far apart. Now, one way that you can really verify that, I'm going to go ahead and get rid of these open circles. We can verify that by taking a look at a table and using the values of x that we wrote out just a moment ago. And the shortcut way to get your table on your graphing scratch pad is to use the shortcut Control-T. And as we discussed earlier, you're going to have to do some table setup here because right now, as you can see, the x values are pretty much defined to be integers as default. So that's an easy fix. Most of the time you would hit the menu button anytime that you want to make some adjustment. It looks like option 2, table, would be a great idea, and option 5, edit table settings. And in the course of watching this video, if you do have your TI Nspire, you can follow along to make sure that you're using the correct keystrokes that I am. I think in this particular instance, we're much better off changing the independent variable to ask. It's very pointless to probably change the table start and the table step since we do not have uniform increments of our x values. Basically, setting the independent variable to ask will blank out all of those x values and give you the freedom to type in exactly what you want. So if you recall from before, we're going to start with, from the very left of our graph, negative 0.1, the very left of our chart, I should say. And then we'll go to negative 0.01, followed by negative 0.001. Not a lot going on there in the y value. Obviously, you could have determined that from the graph. I understand that. You're all smart people. You let x be 0, there's our undefined, and then you will get exactly what you would expect by plugging in the other 3 values, positive 1. So if I were to revert back here to our example, you would fill in the remaining positions with negative 1s and 1s according to our chart from our calculator. And of course, you wouldn't have to have used a calculator for that. But we can see that because these two values differ, right, we're never really converging on a specific value from both the left and the right. They're different, and they will always be different from one another. They will always be negative 1 and 1. We construe that this limit does not exist. Now, I'm going to be a little bit of a stickler. A lot of teachers are a stickler on this as well. A lot of times you're going to have to tell me why it doesn't exist. Okay? And in this particular case, if you've got your notes, you remember from the very beginning of this demonstration, I had a box with 3 different reasons why a limit fails to exist. And we would say it's because the function f of x approaches 2 different values. It approaches 2 different values from the left and right. I know it's a little wordy. You're not going to have to do this very often. That's good news. But when you do, you really want to be very specific in your wording so that you would get full credit. So there's our example 3. Now, if we move forward, we'll take a look at example 4, which I'm going to tell you is going to, again, demonstrate one of the other 2 reasons why a limit fails to exist. All right? You probably can figure this out, especially if you have a pretty good knowledge of the graph of f of x equals 1 over x squared. In fact, my students in my class are asked the summer before they take AP Calculus to sketch the 20 most popular graphs that they might encounter, and 1 over x squared is indeed one of them. So let's remember this box. We'll get back to it in just a moment. But if we go to this example 4, since x is approaching 0, hey, that's great. We can go ahead and use the same values of x that we had before. Okay, we're going to adopt the, what I call, once again, the 1,000th, 100th, 10th approach on both sides. tell my students that a lot of times when you're evaluating a limit numerically, it is sort of a pain because there's a lot of busy work, a lot of writing. But I think it's a very important thing to study at the very beginning of studying limits because it does get you a little bit more comfortable before we do some of the more shortcut approaches. Let's go to the Nspire once again. And there's a variety of things that you can do in this particular instance. If you want to completely turn off the table, you are welcome to do that. If you have the 3.2 operating system, you can now hit Control-T while you're still in the table pane, which is a really nice feature of 3.2. The problem with that is we would have to reset our table to accept X values that we type in, and let's face it, our X values on this table are pretty good, aren't they? Right? We want the exact same X values, we just want a different function. So I would just go ahead and leave the table there, and I would gravitate towards the graphing pane again, and to do that, the shortcut is hitting Control-Tab. That's probably the best way. You can probably see there on the computer screen there how it did highlight the graph. I'll do it again. Control-Tab. Now the table is highlighted. Control-Tab. Now the graph is highlighted. Call up your graphing entry line, Control-G, and I think you're better off just cursoring up, highlighting the F1 row again, and let's just delete this guy. Delete, delete. All right, don't worry if the graph didn't delete yet, it will. And then we can just enter a fraction template, and of course our 1 over x squared. And if we hit enter, it'll regraph. It'll be in the same original color blue, which is defaulted for your initial functions. Blue is a very nice color to see on the TI Nspire. Okay, so there's our graph of 1 over x squared. You're probably used to seeing that. Once again, it's awesome in that if we go back to our table side, and Control-G can do that, we see that, hey, our values are all set to go. I might just want to cursor and kind of take a look, and we'll notice that, if we look at the y, when, oops, I need to go up one more. When we are at negative 0.1, our y value seems to be 100. Special note, I like to focus my attention down here in the gray box to really get the true gist of what that y value is, because it's possible that you could run into some issues here with the side of the table that doesn't reveal everything. And there's other things that you can do. You can widen this particular cell if you wanted to, but I think it's easiest just to look down here. Okay, I'm going to go ahead and get rid of my scripting here so that we can dive into this a little bit more. So if we see that at x negative 0.1 we have 100, at x equal negative 0.01 we have 10,000, and at x equal negative 0.001, what is that? That is 1 million, is it? Count the zeros, 1, 2, 3, 1, 2, 3. So you got 100, 10,000, and a million. So we're going to remember those as we go back to our document, and you would physically fill those in. If I can remember, 100, 10,000, and 1 million. That's certainly an advantage of you having the handheld calculator in front of you, because you can just look directly from the calculator back to the paper for those of you in my class that are taking the notes on this. And then if we return to the calculator and we just pick up where we left off, of course we knew that x can't be 0. We get an undefined. Okay, we get that. But then if we continue to look on the other side, it's just that million, that 10,000, and that 100 in reversed order, as you can see. 1 million, 10,000, and 100. So let's finish our table. Now, what does this say about our limit? If you were to look at these two guys and sort of compare them, yes, you want them to be the same, I understand. It would be very easy for one to say, the limit must be 1 million. Well, you got to be careful there. Is this limit 1 million? If we take a look at the graph one more time, you'll notice that this does nothing but continue to go up and up and up and up and up. I'm going to use my red pen to illustrate that. up and up and up. So I don't think it would be a smart idea to say that the answer is 1 million. In fact, I could go back to my table and maybe get a little closer to 0. Maybe if 1/1000th isn't enough, how about I get there to like maybe 1/10,000th, which is 0.0001. Right? 3 zeros and a 1. 1/10,000th, and you'll notice when I highlight it, the y value is much more. Right? If we count the zeros here, we have, looks like 100 million. We have 100 million on that guy. So think about that. Seems like the more decimal places that we decide to put in right here, the bigger this number is going to get. So you think about that for a limit and for a while and figure out, oh, what is the limit? You think about it for a minute to find the limit, and hopefully you come to the conclusion that this limit will essentially be infinity, positive infinity. And that is one of our rationales for a limit not existing. Okay, I know that's kind of confusing. Hey, it exists. The answer is infinity, right? It's infinity. Well, it's not like infinity is a number. So you're better off going ahead and saying, well, that limit doesn't truly exist because it has this unbounded behavior. And that's exactly what this particular reasoning is saying. F of x increases or decreases without bound as x approaches c. In this case, the function is, the function is obviously increasing. So if we go back and we give a reasoning for that particular limit not existing, we would say that the limit, I'm writing in red here, the limit does not exist because f of x increases without bound. You can probably guess if your graphs went, your end behavior of your curves went downward, sort of to the floor, you would say that the graph would approach negative infinity, and therefore f of x decreases without bound. And we can kind of polish this up by saying as x approaches 0. And yep, it'd be nice if we spell approaches correctly. Okay. One more example. It's one of my longer videos. I understand that, but it's really important, in my opinion, that I showed all three of these together. So we're going to deal with example 5. Fortunately for us, not by accident, that this limit has focused on x approaching 0. What that'll allow us to do is to use the same values for x throughout, and that just really saves quite a bit of time. So we'll get these going in the hopes that these will be good enough for us. We'll find out. Go to our trusty calculator, and we basically do what we did before. We'll highlight the graphing pane by Control G. We'll call up our graphing line by hitting, Control Tab. We'll call up, I'm getting ahead of myself, Control Tab will pull up the graphing screen. Control G will pull up the graphing entry line. Cursor up one time, highlighting the F1 line, delete twice. We'll get rid of it. And then if you recall, that particular function was the sine of quantity 1 over x. So we'll push our trig button for the first time today, and the sine function is our first option. That's nice. And then we can put a fraction template afterwards with a 1 over x, and hit enter and just take a look at what we got. That's kind of interesting. Kind of not what I expected. Perhaps it's not what you expected as well. Right. Let's take a look at this guy. Now, if we jump to the chart, let's say, and obviously I'm going to have to make some adjustments with this because I kind of messed around with that entry line, so I'm going to fix that, if that's okay. We're going to call that positive 0.001, get it back where it was. is it possible if we were to look at the y values very close to when the x value is 0? So that would indicate we're looking at this value here and this value here, the two that I have checked. Do those look like they're approaching a particular value? One's a positive 0.8268 approximately, the other one's a negative 0.8268. Maybe it's a little confusing, and that's okay. That's okay if you're not very confident. I'm going to show you something that you can do with the TI Nspire that you may not have done before. Certainly my students probably haven't done this since we tackled this so early on in the course. I want to zoom in. I want to find out exactly what's going on. I want a little bit more detail. So in essence, what I will do is I will select a region about the size of that rectangular box, and that will then become my entire display here in this window pane. So to do that on the TI Nspire, very simple. We would go into, once again, the menu button. Make sure, though, of course, that the graphing pane is highlighted. Otherwise, you won't get the menu options that you want. And if you hit the menu options, we can see option 4, window zoom. And like I said before, zoom box would be a good option for this one. All right, and it's very simple. It asks you to select where you would want the first corner. That would be the, say, the upper left corner. So the best way to do this is just to kind of use your finger and touch along the mouse pad, and you'll see this magnifying glass show up. And once you are satisfied with that upper left corner, you could hit either enter or the click button. And then it asks you the second corner, which would be a lower right-hand position, and you can start to see a little box appear. And once the action is sort of inside that box nicely, you can go ahead and hit enter, and then you can see what it's done. It is giving us a little bit better view. Now I'm going to do something here. I'm going to hit escape because I want to get out of this zoom box mode. This guy here is probably going to be a little bit of a problem. And I can move him around, but he might even still be a problem later on. So another thing that you can do if you want to get rid of him is to do a little sort of hide control menu. Oops, sorry. Make sure we can get rid of this guy. Doesn't want to go away here. Well, I know delete here is an option. The problem is, if we delete him, it sometimes gives students the impression, oh my goodness, is that going to delete the graph? No, all that is a label. So you could have simply, if I kind of talk you through that again, hit control menu, bring up the delete option. I tell my students a lot, and a lot of really good Cube instructors have re-emphasized this. Hitting control prior to menu is sort of like right-clicking a mouse. It gives you a whole new set of options that you can choose from. Now I'm going to go ahead and do another zoom with this. So menu, window zoom, zoom box, because I would really like to see what's going on in this particular area. Maybe that helps, maybe it doesn't. All right, let's zoom again. We're already in the zoom mode, so we can just roll back up to the first corner. And it doesn't matter if you use the top left or lower right. I like to go the top left first myself. And let's see if this helps. And maybe that doesn't help. I don't know. I'm going to stop right there because if I do this anymore, it's going to look like one of those UPC labels that you find on products. But what's going on here is if I were to use the red pen and you kind of watch along from the left side, this graph, as I kind of overwrite the blue, is just bouncing back and forth, getting a lot more active, a lot more active, a lot more active. The question is it ever going to reach it where an x value is 0? All right, well, think about that. This is kind of where I wish I had the function still back up so you could see it, but no worries. You can look right here. Can x be 0 right there? What do you get if x is 0? The sign of 1 over 0, the sign of something that's undefined. Well, guess what? That's undefined also. And what's going on, if believe it or not, in this particular sketch, is that this curve is just bouncing back and forth, even from the right side. I'm going to do that one in green. It will oscillate back and forth, getting more and more active, but it will never, ever reach the origin. It will never reach the position where x is 0. Sometimes that's a difficult thing to understand, but things can constantly be moving towards a destination and never reach it. Right? It's a very bizarre concept. I could challenge you guys to think about this. Pretend that you have your finger outstretched or reached out in front of you where a wall is about, say, 10 feet away. And let's say that every second that goes by, you walk towards that wall by, say, half the distance. The next second, you walk towards it and cut the distance in half again. I ask you, would you ever touch the wall? Well, it might look like you're touching the wall after a while, but really, in theory, if you just cut the distance in half, you will never, ever make contact with that wall, and you can do that forever and ever and ever. And this particular problem is sort of similar. Okay? Now, if we go back here to the document, it's going to be a little tougher for me to remember these values that we have in the chart, so I'm going to kind of leave it to you guys to figure out exactly what you would want to be putting in these boxes. If you have any type of calculator, graphing calculator or scientific calculator, you could figure those out. But because we've determined the fact that the function oscillates between two fixed values, we're going to say that this limit doesn't exist. So again, limit doesn't exist. Want a reason though, and that reason is exactly what I explained a moment ago. F of x, the function, the y values, here's an interesting word, oscillate, means sort of to go back and forth. It oscillates between two fixed values. As x approaches 0. And if we visit just one last time the three reasons, we can see that that's pretty much word for word what number 3 has. So hopefully this video was a little bit helpful. I know it was a bit lengthy, but as you really put the finishing touches on finding limits in a graphical and numeric or table approach, it's really important to see examples like these three, because teachers like to throw these at you because that's what kind of makes you think, get on your toes a little bit. And at the point that you kind of feel comfortable with these types of limits, you're probably going to be better off handling the ones that you have to do analytically, which would not allow you to use a calculator. So anyway, it's been fun. Hope you enjoyed this, and we'll see you next time.